Right, Assalamualaikum and hello everyone. So in the previous session, we have looked at Euler's method, and for this session, we're going to look at Taylor's method. So quite similar with Euler's method. In order to solve the ODE using Taylor's method, there are two things that you need to do. First is you write Taylor's equation, and second, you prepare the table. Please note that for Taylor's equation from the Taylor series, we will consider up until the second order. So the equation is a bit different from, it has an extension from the Euler's method, and when we consider until the second order, so when we prepare the table, there are two additional information that we need to put, which is y double prime and h squared over 2 factorial y double prime. Alright, so let's use the same example in the Euler's method, whereby the ODE is given as 2y prime plus 3y is equals to e to the power of 2x. So find y when x equals to 1, given that the initial condition x equals to 0 and y equals to 1. Use Taylor's method and assume step size of h equals to 0.2. Okay, so it's the same example as before, it's just that we want to use Taylor's method. So first, what we need to do is we write Taylor's equation, whereby Taylor's equation is given as y xi plus 1 is equals to y xi plus h y double prime xi, an additional one to the Euler's method. For Taylor's equation, we've got h squared over 2 y double prime xi. Okay, so this is the Taylor's equation. Okay, if you can still remember, Euler's method is up until here only, but if you're using Taylor's equation, we need to consider until the second order. Alright, next we prepare the table. So if you can see, if we compare to the Euler's equation, we have two additional terms here, which is h squared over 2, and the second one is y double prime. So this is the additional information that we need to put in our table. So the table is almost the same with Euler's method. Okay, we have I, then we have x, and then we have y, we have y prime, we have h y prime. Okay, so Euler's method up until here, but since we are using Taylor's method, we will have another two information, which is y double prime and h squared over 2 y double prime. Okay, then we know that the step size is 0.2 and x is starting from 0. So the second one will become 0.2, 0.4, 0.6, 0.8, and until 1, because we start from 0 until x equals to 1, and then I input all the iteration from 0, 1, 2, 3, 4, 5, and then the y value is given as 1 when x equals to 0, so this is 1. So this is the information that we obtain, and then next we need to find the y prime here. So how do we get this value is we need to input this equation in our calculator, because we are considering about y prime, so make this as a subject. Thus y prime is equals to e to the power of 2x minus 3y over 2. Input that value in your calculator, and then hy prime is just a matter of 0.2 multiplied by the value of y prime that we're going to obtain. And then the second tricky part is the y double prime. So how do we get this y double prime? So if y prime is equals to this, so y double prime is just a matter of differentiate it by another term, by one more time. So if I differentiate this equation, I will get 2e over 2x minus 3y over 2. Okay, so this is the equation for y double prime. So what I can observe is that most students, okay, when they don't have a strong fundamental in mathematics, they don't know how to differentiate the equation, so you will probably stuck here. And then to find this value, it's just a matter of 0.2 to the power of 2 multiplied by the value of y double prime. So to make things simple, in our term we will use x as x in our calculator, the y we will use as y. Okay, y prime we're going to replace it with a, hy prime as b, y double prime as c, and h squared over 2y double prime as d. So how do we find the value of a here? Again, as I mentioned, input this in your calculator. So this one is actually our x value and this is y value. Okay, so input that in your calculator, and then when you press the CLC button, so the x value here is 0 and the y value here is 1. Okay, so when I solve using my calculator, I'll get the value of negative 1. So to find the value of p here, hy prime, so 0.2 multiplied by our y prime value, which is negative 1. So I'll get negative 0.2. And then next, how do I find the value of y double prime here? So input this in our, sorry, I missed this one. This one should be minus 3y double prime, because if we differentiate y by one time, we'll get y double prime. So now in our calculator, this equation will be transformed to 2e to the power of 2x minus 3, because it's y prime. So y prime we used a here over 2. So input in your calculator, the x value is 0 and the a value is negative 1. So I will get the value of 2.5. Okay, And then next, how do I find the D value for the first row? So put this one, multiply by our y double prime, which is this one. I'll get the value of 0.05. Okay, I want everyone to do this on your own so that you will understand. So now we have completed the first row. Next, how do we find the y value for the next iteration? So this is where Taylor's equation can be used, whereby Taylor's equation is given as this one. So you can input in your calculator, okay, yxi, we use the value of y, okay, plus hy prime, we use as b, and h squared y double prime is d. So y plus b plus d is actually 1, okay, y plus b, our b value is negative 0.2, plus d value is 0.05. I will get the value of 0.85. Okay, next we need to obtain our new value of a. So again, we use this equation. So our x value now has changed to 0.2, and our y value is now 0.85. So if I use my calculator, I will get negative 0.5291. So hy prime is 0.2 multiplied by negative 0.5291. I get 0.1058. So y double prime, I use this equation. So the x value now is 0.2, and our a value is negative 0.5291. So I'll obtain 2.2855, 0.0457. Okay, so after I completed that, I can find the value of y at the next iteration. Again, I just call back this function from my calculator. So our y value is 0.85. Our b value is negative 0.1058, and our d value is here. So basically it's 0.85 plus negative 0.1058 plus 0.0457. So the answer is 0.7899. Okay, so fast forward. Okay, next repeat the same thing, find the value here. I get negative 0.0721, negative 0.0144, and then 2.3337, 0.0457, 0.8222, 0.4268. I want everyone to do this by yourself. Yeah, I'll just fast forward everything. 2.6799, 0.0536, 0.9612, 1.0347, 0.2069, 3.401, 0.0680, and then the value that we're going to find is 1.2361. Okay, so this is the answer if we use Taylor's method. Alright, so in this example, so it have give us the exact solution, whereby the exact solution is given as yx is equals to 1 over 7 e to the power of 2x plus 6 over 7 e to the power of negative 3 over 2x. So if we input the x value, because we want to know the exact solution, so x value, because the question asks us x equals to 1, find the y value. So replace in your calculator this value as 1. So I will get the answer of 1.2468. Now let's analyze few things. So from the exact solution, the value is 1.2468. From Taylor's method, I'll get the value of 1.2361. And if we compare with Euler's method, okay, the results that we obtain is 1.0800. So from here, you can see that the Taylor's method, the answer is more closer to the exact solution, while the Euler's method is a bit far from the exact solution. So why do you think this is possible? Why that Euler's method, the answer is a bit far from the exact solution compared to Taylor's method? The reason lies from the Taylor series, because in Taylor's method we consider up until the second order in our Taylor's equation, but for Euler's method it is only up until the first order. So that's why Taylor's method is more accurate compared to the Euler's method. Alright, that's all for me for this session. So I hope to see you again. Bye.